Let us see about particle size and texture studies in material characterization. Particle size and texture studies. What is particle size? Particle size is a measurement of the size of individual particles that make up a material. It can be applied to a solid, liquid, and gaseous particles. It is a notion introduced for comparing the dimensions of solid particles, liquid particles, and gaseous particles. Particle size considerations. In particle size measurements, the particle size is usually measured in microns, where 1 micron is 1/1000 of a millimeter. The most common way to measure particle size is with a particle size analyzer. Particle size application. Particle size is important in many industries including food, chemical, pharmaceutical, and cosmetics. Particle size distribution. Particle size distribution is PSD. It is the range of size of particles in a material. Particle size categories. It ranges from nanometers to millimeters, and they can be grouped into categories like boulders, cobbles, gravel, sand, slip, and clay. Particle size is usually measured using the Debye-Scaler method, and the Debye-Scaler formula is D is equal to K lambda by beta cos theta, where K is the shape factor, which is approximately 0.9 for most of the materials. Beta is the full width at half maximum, which is FWHM of a diffraction peak. Lambda is the wavelength of the X-ray, and theta is the Bragg angle. Working of the Debye-Scaler method. In X-ray diffraction, when the X-rays interact with a crystalline material, they are diffracted in a specific way depending on the arrangement of atoms within the crystal lattice. Powder sample. The Debye-Scaler method typically uses a powdered sample where the crystals are randomly oriented, ensuring that all possible crystal planes are exposed to X-ray beams. Diffraction pattern. The diffracted X-rays form a series of concentric rings on a photographic film or detector, which are then analyzed to determine the crystal structure. Analysis. The positions and intensities of these rings provide information about the spacing between the crystal planes. Now we can calculate the particle size of the sodium chloride sample using this Debye-Scaler method. Here we can see the graph of the XRD graph of the sodium chloride. In this you can observe that the HKL plane 200 is the highest peak. So we are considering that and measuring the particle size of sodium chloride. So lambda is equal to 1.5406 angstrom, beta is equal to 0.5 degree for the 200 peak, theta is equal to 31.7 degree, K is equal to 0.9. So when we are substituting these values in the Debye-Scaler formula, we get D is equal to 34.6 nanometer, and which is the particle size of the sodium chloride sample. Advantages. It is simple and rapid. The Scaler equation is a straightforward method for estimating crystallite size, requiring only XRD data and a simple calculation. It is non-destructive, as it meaning the sample remains intact after the measurement. Bulk analysis. It provides information about the average crystallite size across the entire sample, unlike microscopic methods that provide local information. And it is also cost effective, and it can be used for multiple applications. Disadvantages. It is limited only to nanoscale crystallites, and it is most accurate for estimating the size of very small crystallites, and its accuracy decreases with the increasing size. It requires sample preparation. Samples need to be prepared for XRD analysis, which can be time consuming and require specialized equipment. Doesn't account for strain and imperfections. The equation assumes that peak broadening is solely due to crystallite size, ignoring the influence of strain, crystal imperfections, and other factors. and it is not suitable for large particles. The scalar equation is not applicable to grains larger than about 0.1 to 0.2 micrometer, which preludes those observed in most metallographic, thermographic microstructures. Let us see some of the application of the particle size. It can estimate the average size of the crystals, and in material characterization it can be used to characterize the microstructure of materials, including nanoparticles, catalysts and other materials. It identifies and quantifies the different phases in a material, and also monitors the changes in crystallite size during the synthesis or processing of the material. Let us move on to the texture studies. Texture studies in material characterization involve analyzing the orientation, distribution of crystals within a material, which can be done using techniques like X-ray diffraction, electron backscatter diffraction and neutron diffraction to understand how texture affects material properties. Texture is a key in determining the anisotropy of a material, meaning that its property can vary depending on the direction. So, why do we need texture studies? Texture studies to understand the processing history. That is, the texture of a material reveals information about its manufacturing history, such as deformation, annealing, or other processing steps. To predict its behavior, texture analysis can help predict how a material will behave under different conditions such as stress or deformation. Optimizing properties. By understanding and controlling texture, engineers can optimize material properties for specific applications. Techniques for texture analysis. Texture analysis. The texture of a material can be analyzed using various techniques such as X-ray diffraction, electron backscatter diffraction, neutron diffraction, pole figures and inverse pole figures, crystal orientation distribution function. X-ray diffraction. It is a common technique to probe the material and a diffraction pattern where the X-rays are used to probe the material and the diffraction patterns are analyzed to determine the orientations of the crystal. In electron backscatter diffraction, instead of X-rays, electrons are used to probe the material. In neutron diffraction, neutrons are used instead of X-rays. Pole figures and inverse pole figures, they are the graphical representation of the texture data showing the distribution of crystal orientation. Crystal orientation distribution function is a mathematical representation of the texture data, allowing for a more quantitative analysis. Let us see some of the applications of texture analysis. Metals. Controlling the texture of metals like steel and aluminum is crucial for achieving desired properties like mechanical strength and formability. In geology and mineralogy, the studying of texture of rocks can help understand the Earth's deformation history. In thin films, optimizing the texture of thin films can be important for applications like hard disk drive materials or superconducting wires. In food industries, texture analysis is used to characterize the sensory properties of food products. In pharmaceuticals, it is used to characterize the textures such as tablets, gels, powders, granules, capsules, tubes, and sachets, syringes, and other medical devices. In cosmetics, it is used to characterize the texture of cosmetics, skincare, and personal care products, powders, creams, waxes, and gels. In adhesives, it is used to characterize the texture across various sectors, not forgetting paints and polymers. So, in conclusion, we have learned what is particle size, its application, its advantages, how it is measured using the Debye scalar method, the texture analysis, and its application. Thank you.